preparing for a microservices interview. You've reached Interview Guide, and this video is for you. We'll walk through 21 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What are microservices, and how are they different from a monolithic architecture? Microservices are small, independently deployable services organized around business capabilities. In a monolith, modules share one codebase, database, and deployment pipeline. Microservices split those responsibilities so teams can build, deploy, and scale independently. The benefit is agility and isolation. The cost is distributed system complexity like latency, tracing, data consistency, and failures across networks. I would choose microservices only when organizational scale and domain complexity justify that overhead. While answering, focus on independent deployability, business capability boundaries, decentralized data ownership, operational complexity, communication overhead, team autonomy, and why microservices are an architectural trade-off, not a default upgrade. Question 2. When would you avoid using microservices? I would avoid microservices when the team is small, the domain is still changing heavily, or the organization lacks mature DevOps practices. Microservices require automation, observability, service ownership, and strong API discipline. Without those, teams just create a distributed monolith that is harder to debug and deploy. A modular monolith is often better early on because it keeps boundaries clean while avoiding network, consistency, and operational complexity. Make sure to cover team size, domain maturity, deployment discipline, monitoring readiness, operational cost, premature distribution, and why a well-structured modular monolith can be a better starting point. Question 3. How do you decide service boundaries in a microservices architecture? I usually start from business capabilities, not tables or technical layers. Domain-driven design helps identify bounded contexts such as ordering, payment, inventory, and shipping. A good service owns its data, exposes clear APIs, and changes mostly independently from other services. If two services constantly require coordinated deployments, the boundary is probably wrong. I also consider team ownership and operational responsibility, because Conway's Law strongly affects microservice success. In your answer, talk about domain-driven design, bounded contexts, business capabilities, data ownership, coupling, change frequency, team ownership, and avoiding boundaries based only on technical layers. Question 4. How do you choose between synchronous and asynchronous communication between microservices? Synchronous communication, like REST or gRPC, is useful when the caller needs an immediate response, such as checking product availability during checkout. Asynchronous messaging works better for workflows that can complete later, like sending emails or updating analytics. Sync calls are simpler, but increase runtime coupling and cascading failure risk. Async communication improves resilience and decoupling, but introduces eventual consistency, retries, duplicate messages, and harder debugging. Be sure to mention REST, gRPC, messaging, event-driven design, latency, coupling, reliability, user-facing requests, eventual consistency, backpressure, and how communication style impacts failure handling. Question 5. What is the role of an API gateway in microservices? An API gateway is the entry point for clients into a microservices system. It routes requests to the right services and often handles cross-cutting concerns like authentication, rate limiting, TLS termination, request logging, and response aggregation. For example, a mobile app may call one gateway endpoint that gathers profile, orders, and recommendations. I keep business logic out of the gateway, otherwise, it becomes another monolith at the edge. While answering, cover request routing, authentication, rate limiting, protocol translation, aggregation, TLS termination, observability, avoiding business logic in the gateway, and differences from a load balancer. Question 6. How does service discovery work in a microservices environment? Service discovery solves the problem that service instances are dynamic. Containers can start, stop, scale, or move across nodes, so hard-coded hostnames do not work. A registry, or Kubernetes DNS and services, lets callers find healthy instances by logical name. Discovery can be client-side, where the caller chooses an instance, or server-side, where a load balancer routes traffic. Health checks are essential so traffic avoids unhealthy instances. Make sure to cover dynamic service instances, service registry, client-side versus server-side discovery, health checks, Kubernetes service discovery, load balancing, and why static configuration fails at scale. Question 7. Why is database per service recommended? And what problems does it create? Database per service means each service owns its schema and controls all access to its data. This prevents tight coupling through shared tables and lets teams evolve schemas independently. The downside is that joins across services disappear. Reporting becomes harder, and consistency is no longer automatic. To share data, services expose APIs or publish events. I prefer this model for autonomy, but I design carefully for duplication, eventual consistency, and data governance. In your answer, discuss data ownership, loose coupling, schema independence, avoiding shared databases, consistency challenges, duplication, reporting complexity, transactions, and how events or APIs synchronize data. Question 8. How do you handle distributed transactions in microservices? In microservices, I avoid traditional distributed transactions because two-phase commit creates tight coupling and availability issues. Instead, I use the saga pattern. A business workflow is split into local transactions, and each step publishes an event or calls the next service. If a later step fails, compensating actions undo earlier effects, such as refunding a payment. The key is designing idempotent steps, durable state, retries, and clear failure recovery. Be sure to explain why two-phase commit is avoided, how saga patterns work, orchestration versus choreography, compensation actions, idempotency, failure recovery, and eventual consistency trade-offs. Question 9. What is eventual consistency, and how do you explain it to stakeholders? Eventual consistency means data may not be immediately identical across services, but it converges over time if no new updates occur. For example, after placing an order, payment may confirm immediately, while inventory and shipping update seconds later. I explain this in business terms. Some workflows tolerate short delays, while others require strong consistency. Good design includes status states, reconciliation jobs, clear user messages, and monitoring for stuck updates. While answering, focus on consistency versus availability, asynchronous propagation, user expectations, stale reads, reconciliation, business tolerance, examples like order status, and designing clear UX around delay. Question 10. How do you make microservices resilient to failures? I assume every network call can fail, hang, or return slowly. Resilience starts with strict timeouts, bounded retries with exponential backoff, and circuit breakers to stop calling unhealthy dependencies. Bulkheads isolate resources so one failing service does not exhaust all threads or connections. For non-critical paths, I use fallbacks or cached responses. The goal is graceful degradation, not perfect availability, because cascading failures are usually worse than partial functionality. Make sure to cover timeouts, retries with backoff, circuit breakers, bulkheads, fallback responses, rate limits, load shedding, health checks, chaos testing, and avoiding cascading failures. Question 11. What observability practices are essential for microservices? Microservices need observability because a single user request may cross 10 services. I always want 3 pillars: logs, metrics, and traces. Logs should be structured and include correlation IDs. Metrics should track latency, traffic, errors, saturation, and business indicators. Distributed tracing shows the path and timing of a request across services. Without these, teams guess during incidents. With them, they can isolate bottlenecks and ownership quickly. In your answer, discuss centralized logging, metrics, distributed tracing, correlation IDs, structured logs, service-level objectives, dashboards, alerts, RED or USE metrics, and production debugging. Question 12. How should CI/CD work for microservices? Each microservice should have its own CI/CD pipeline, so teams can build, test, and deploy independently. A typical pipeline runs unit tests, integration tests, contract tests, security checks, builds a container image, and deploys through environments. For production, I prefer canary or blue-green deployments with fast rollback. Feature flags help decouple deployment from release. If every service must deploy together, the architecture behaves like a monolith. Be sure to mention independent pipelines, automated tests, container builds, contract validation, deployment strategies, rollback, feature flags, environment promotion, and why one shared release train reduces microservice benefits. Question 13. How does Kubernetes help in running microservices? Kubernetes provides the operational platform for running many containerized services. It handles scheduling, service discovery, load balancing, rolling updates, health checks, restarts, and horizontal scaling. Deployments manage replicas, services provide stable networking, and config maps or secrets externalize configuration. However, Kubernetes does not automatically fix bad service boundaries, poor observability, or unsafe deployments. It gives strong primitives, but teams still need disciplined architecture and operations. While answering, cover container orchestration, deployments, services, auto-scaling, self-healing, rolling updates, config maps, secrets, ingress, resource limits, and what Kubernetes does not solve automatically. Question 14. How do you handle API versioning in microservices? I treat API versioning as a compatibility problem first. The safest changes are additive, new optional fields, new endpoints, or relaxed validation. Breaking changes need a new version, clear deprecation timelines, and communication with consumers. Versioning can be in the URL, headers, or media type, depending on standards. I also use consumer-driven contract tests, so providers know when they might break clients before deployment. Make sure to cover backward compatibility, consumer impact, semantic versioning, URL versus header versioning, deprecation policies, contract tests, additive changes, and supporting multiple client versions safely. Question 15. How do you secure communication between microservices? I do not assume internal traffic is trusted. Services should authenticate callers, authorize actions, and communicate over encrypted channels. For user-facing flows, OAuth 2 and JWTs are common, but internal service identity may use MTLS or a service mesh. Secrets belong in a managed vault or secrets manager, not environment files in source control. I also apply least privilege, network policies, and audit logs for sensitive operations. In your answer, talk about authentication, authorization, OAuth 2, JWT, MTLS, service identity, zero trust, secrets management, least privilege, network policies, and auditing internal calls. Question 16. What is idempotency and why is it important in microservices? Idempotency means performing the same operation multiple times has the same final effect as performing it once. It matters because retries, timeouts, and message redelivery are normal in distributed systems. For example, a payment service should not charge a customer twice if the client retries after a timeout. I typically use idempotency keys, unique constraints, and state checks to make operations safe under duplicates. Be sure to explain duplicate requests, retries, message redelivery, idempotency keys, safe state transitions, payment examples, database constraints, and how idempotency improves reliability. Question 17. A downstream payment service is slow during checkout. How would you handle it? First, I would enforce a strict timeout so checkout threads do not pile up. Retries should be limited and use backoff, because aggressive retries can amplify the outage. If payment is temporarily slow, I may move the order into a pending payment state and process asynchronously through a queue. A circuit breaker protects the system when failures spike. I would also monitor latency, error rates, queue depth, and customer impact. While answering, cover timeout budgets, circuit breakers, retries with backoff, async processing, user experience, queuing, fallback states, monitoring, graceful degradation, and preventing resource exhaustion. Question 18. How do you manage configuration and secrets across many microservices? Configuration should be externalized from code, so the same artifact can run in different environments. Non-secret settings can live in config services, Kubernetes config maps, or environment variables. Secrets should be stored in systems like Vault, AWS Secrets Manager, or Kubernetes Secrets with proper encryption and RBAC. I avoid hard-coding credentials, support rotation, and audit access. Dynamic reload is useful, but critical changes still need careful rollout. Make sure to mention externalized configuration, environment-specific settings, secret rotation, vault tools, encryption, avoiding hard-coded values, dynamic reload, access control, and auditability. Question 19. What testing strategy would you use for microservices? I use a layered testing strategy. Unit tests cover business logic quickly. Integration tests verify databases, queues, and framework wiring, often with test containers. Contract tests are critical because services evolve independently and consumers need compatibility guarantees. End-to-end tests should cover only the most important user journeys, not every edge case, because they are slow and brittle. The goal is fast feedback with enough confidence to deploy independently. In your answer, cover the testing pyramid: unit tests, integration tests, contract tests, end-to-end tests, test containers, mocks, staging environments, and avoiding brittle full system test suites. Question 20. How would you scale one hot microservice without scaling the entire system? I would first confirm the bottleneck with metrics and profiling, because scaling the wrong layer wastes money. If the service is stateless, I can increase replicas behind a load balancer or use auto-scaling based on CPU, latency, or queue depth. If the database is the bottleneck, I may add caching, indexes, read replicas, or partitioning. For bursty workloads, queues can smooth traffic and protect downstream dependencies. Be sure to cover independent deployment, horizontal scaling, stateless design, database bottlenecks, caching, partitioning, auto-scaling metrics, queue-based load leveling, and performance profiling before scaling. Question 21. How would you migrate a monolith to microservices safely? I would avoid a big bang rewrite. A safer approach is the strangler fig pattern. Route selected functionality from the monolith to new services gradually. I start with clear seams, usually a business capability with manageable data ownership. An anti-corruption layer protects the new service from monolith assumptions. Database separation is often the hardest part, so I migrate carefully using events or APIs. Strong observability and rollback plans are mandatory. While answering, discuss incremental migration, strangler fig pattern, identifying seams, extracting by business capability, database decomposition, anti-corruption layers, observability, rollback, and avoiding big bang rewrites. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.